Hello and welcome to today's lecture on job machine scheduling under the module of operations management. Today's lecture will be based on a Johnson's algorithm, which is very beneficial algorithm for job machine scheduling, especially in multi-variety manufacturing. So what happens in multi-variety manufacturing? Several variety of products are there having variable processing time but have a specific sequence of operation. Okay, so if we take the example of a biscuit manufacturing company, so every biscuit has some sequence of operation. There is a dough mixing process, then there is the addition and mixing process of all the ingredients of that biscuit, then there is a molding process, then there is drying process, then there is packaging process. But there are multiple variety of biscuits are there. Some are plain biscuit, some are fiber biscuit, cream biscuit, like that. So when there are multiple variety of products but having a specific sequence of operations to be performed on every job, so we have to do the scheduling of which job is to processed on which machine. Okay, so continuing further, the agenda of today's lecture is job machine scheduling. So which job is to be performed on which machine? The schedule of this particular type is called as job machine scheduling. Then we will learn about the Johnson's algorithm, then steps of Johnson's algorithm for a two machine problem. We will try to understand this particular concept with the help of industrial case. Then we'll see what to do when there are more than two machine, that is 3 machine. We'll also see if there are n number of machines in such setup, then how to proceed with Johnson's algorithm, or is it possible or not. Then there are some tie breaking rules for Johnson's algorithm which are very beneficial. We will discuss on this in detail. So starting with the job machine scheduling, so the conversion of finished goods from raw material consists of several operations to be performed, that too in a given sequence. Okay, so sequence of operation here is very important. We cannot violate the sequence of operation. For example, packaging operation must be there in the last. We cannot perform that operation first, logically also. Similarly, in the intermediate operations also, the operations are dependent on each other. So there is a definite sequence for the operation, and here the common operations are required for several products are at the same workstations, and the task is to determine the preferred order of products so as to optimize the output in terms of cost, time or profit. What this means, that there are 3 variety of product, let's say A, B and C. Now all the products A, B and C have their definite sequence of operation, and definitely there are some common operations. There is a common machine on which all the 3 products are to be processed. So what is the schedule? When job A will come to machine 1, when job A will go to machine 2, then when job B will come to machine 1, when job C will come to machine 1. In this case, in this way, we have to see by what schedule the entry and exit of job on every machine is to be done. So the Johnson's algorithm, which we are discussing in this lecture, helps us to do this. It gives us the optimum sequence. Okay, that in this particular machine, what will be the sequence by which the job will come, when it will go out. Okay, so in time of every job, out time of every job, that is called a schedule, right? Whenever we call something as a schedule, definitely it has time values involved in it. So first the sequence is also there and the time is also there, that job A will go to this machine at this time, it will exit this machine at this time, then it will go to next machine at this time. That is called as schedule. So it is very simple to understand that this sequence and this schedule is very important for optimizing our output. Otherwise what will happen, there will have a waiting times. Okay, if the scheduling is not proper, what will happen, some operation is getting performed, other product is waiting, which is the direct wastage of time. Okay, and time is then converted into cost. Okay, so the problem becomes very complicated when the several workstations serve many product. As I said, there are, let's say there are two machines A and B, or we can say there are two machines 1 and 2, and there are 3 to 4 jobs A, B, C, D. So the complexity is, for machine 1 all the jobs are to be processed on machine 1, all the jobs are to be processed on machine 2 also. Okay, so how to schedule this? Okay, so in such a problem, the general criteria as per the logic of operations management is always minimum processing time. Okay, so we will first give priority to the job which has a lesser processing time. Okay, so let us see how the Johnson's algorithm solves this problem or helps someone to solve this problem. So the general scheduling problem is stated that there are n jobs, okay, n1, n2, n3, कितने भी jobs हो सकते हैं, which are to be processed on m machines. So the order of machine, that is process sequence, and the process time is given. See, we cannot decide the sequence or we cannot change the sequence because the sequence is logical. If the product is following that sequence, then only it will manufacture. Otherwise, if any operation is reversed or some operation is skipped, we cannot say that product as a finished good. So process sequence is not in our hand, processing time is not in our hand. It is already calculated or decided by the type of operation to be performed and basically a preliminary time study. So process sequence of all jobs are same, but the processing time for various jobs on a machine may differ. Okay, there is a variety of product. So as I was talking about the biscuits, the glucose biscuit takes lesser time than the cream biscuit because there is a change in design. The product variety has a different type of complexity, and due to which the processing times are different for different variety of product. So the problem is to determine the order of processing of n jobs so that the total elapsed time for all the jobs will be minimum. Now what is this total elapsed time? See, as a company or as a customer, there are two perspectives. When we are a customer, we choose a variety, and in our mind that variety is of highest value because I have chosen this variant, so it is very important for me. But for a company, the overall importance of every variety of product is similar. So company is not interested in the processing time of a particular variety, but they are interested to optimize the total elapsed time. Okay, whatever the order I am getting, that may have out of 160 jobs of variety 1, 20 jobs of variety 2, another 20 of variety 3. Okay, so company is not interested in which variety is getting manufactured, but the company is overall interested in optimizing the total elapsed time. Total elapsed time means the time from start to the end of completing all the jobs. That is called as total elapsed time. We will see. So optimizing the total elapsed time means we will keep the total elapsed time minimum. If the total elapsed time is minimum, or you are making effort to keep it minimum, it means that you are optimizing the system. And optimizing the system eventually means maximizing the profit, minimizing the wastage, and several such benefits. So now we will try to understand what the Johnson's algorithm is. So some of the assumption or postulates of Johnson's algorithm are listed over here. I'll read it out. If an operation is absent in a job, then processing time of that operation is assumed as 0. This is but obvious. There is a possibility that in some variety of products some operation is not essential or not necessary. So at such time we will take the value as 0. If the current machine is free, if the job from the previous machine is pending, it cannot start, because as I said, there is dependency in the operation. Okay, I would like to quote the example of mechanical engineering, that the operation of boring, B-O-R-I-N-G, okay, operation of boring can only be performed after drilling. Okay, जब तक ड्रिलिंग नहीं होगा बोरिंग ऑपरेशन हो ही नहीं सकता है. सो इवन इफ द बोरिंग मशीन इज फ्री, इट हैज़ टू वेट, बिकॉज जो पिछली मशीन है ड्रिलिंग मशीन, वहाँ से प्रोडक्ट आया ही नहीं है. So that machine has to wait. It is one of the assumption of Johnson's algorithm. Then no machine can process more than one job at a time. That is a basic assumption. एक machine एक time पे एक ही job process करेगी. Then processing times are independent of processing of jobs. Yes. Each job once started on one machine is continued till the completion on it. So we cannot stop the job in half operation. So if we have two machine, if the job is started operating on machine 1, definitely वो complete होके ही machine 1 से बाहर आएगा, उसके पहले machine को रोकना allowed नहीं है. And the time involved in moving the job from one machine to another, यहाँ पे जॉनसन्स एल्गोरिदम में ये जो टाइम होता है एक मशीन से दूसरे मशीन पे ले जाने का, जो हैंडलिंग टाइम होता है, उसको यहाँ पे निगलेक्ट किया गया है. And this is generally because of the reason that if the machines are closely spaced together, आसपास ही है सब, एक walking area में है, तो वो time काफ़ी seconds में होता है, and it can be neglected at least for calculation purpose. What you can do to compensate it, that after your planning gets over or scheduling gets over, you can add some allowance for this in percentage, so it becomes easy for calculation if we neglect this transfer time or material handling time. Now what are the possible scheduling problems in Johnson's algorithm? So there is n jobs 2 machine problem, n job 3 machine problem, then 2 job m machine problem, n job n machine problem. Out of this, first 2 are very important in calculations, and we will see the 2 machine problem in detail, and we will take a glimpse of 3 machine problem and n machine problems. Okay, so we will first discuss about n jobs. The jobs can be 4, 5, 6, 7, 8, as much as required, and 2 machine problem. So there will be 2 machine, m1 and m2, and there will be variety of jobs. Now we have to do the scheduling, means which job will enter to which machine and when. When means a time factor. Okay, so first there are the steps of Johnson's algorithm. Before that, you see on the right side palette is there. So such palette is there in which we decide the sequence by which the jobs will enter. And about timings, we make a separate table for timing. So there are 2 things which are to be prepared in the Johnson's algorithm. One is this palette. This palette will give you the sequence. We will see in the forthcoming slides that how this palette provides us the sequence. Okay, and after this palette, we assign the timings for every job. So this collectively, palette and that timing table collectively means the job machine scheduling. Okay, जब तक वो उसमें टाइमिंग्स नहीं आएंगे तब हम उसको मशीन शेड्यूलिंग नहीं बोल पाएंगे, अदरवाइज सीक्वेंस विल बी गिवन बाय द पैलेट. Okay, so there are some rules. So first of all, the rule is these are the rules for allotting the job to the palette. Okay, so first of all, we will see the jobs, how many jobs are there. Let's say 5 jobs are there, and how many machines. As we know, this is a 2 machine problem, so 5 jobs are to be performed on 2 machines, M1 and M2. So first of all, we will see the processing time. Okay, we will tabulate the processing time of all the jobs for both the machines, and there are 2 criteria. If the minimum processing time is there in machine 1, then allocate the job first in the palette. Okay, this is a palette. तो अगर आपका प्रोसेसिंग टाइम मशीन 1 में मिनिमम है तो आप जॉब को लेफ्ट साइड से, यानी फर्स्ट में if we always move from left to right, so this is first and this is last. Okay, so you assign the job first in the pallet. But if the minimum processing time is in machine 2, so you assign the job last in the pallet, that is right in the pallet. Okay, and this for every iteration, जो जॉब अलॉट हो चुका है उसको हमको रिमूव करके यही स्टेप्स को फॉलो करना है. Definitely this thing will get clear in the industrial case further. Okay, so this is the industrial case. यहाँ से हम समझने की कोशिश करेंगे that by these rules how this pallet gets filled and how to do this. Okay, how to execute the Johnson's algorithm for a 2-machine problem. So we will try to understand the Johnson's algorithm with the help of this industrial case. So a toy manufacturing factory having 5 varieties of toy to be manufactured on 2 machines sequentially. So the sequence of operation is already known. First on the assembly center M1 and then on the testing center M2. So the processing times of different toys are given below. So they determine the sequence of processing and job machine scheduling. Okay, जॉब मशीन शेड्यूलिंग का एक चार्ट बनाना है और एक सीक्वेंस बताना है, दैट इज आवर पैलेट. सो हाउ टू प्रोसीड नाउ? स्टेप नंबर 1 इज फाइंड द मिनिमम अमंग्स ऑल प्रोसेसिंग टाइम. सी दिस कॉलम, आई विल शो यू द लेजर पॉइंटर फॉर अंडरस्टैंडिंग. दिस कॉलम इज प्रोसेसिंग टाइम ऑफ मशीन 1. दिस कॉलम इज प्रोसेसिंग टाइम ऑफ मशीन 2 फॉर ऑल द जॉब्स A, B, C, D, E. So what the rule says, if the minimum processing time is in machine 1, you allot the job first in the pallet. If the minimum time is in machine 2, you allot the job last in the pallet. So we can see here, what is the minimum processing time? It is 1. Agreed? You can see out of all, minimum processing time is 1. So for 1 for which job? Job B. So as the minimum processing time, that is 1, is in machine 1, that's why we have allotted B to the left, okay, to the first of the pallet. So B is allotted. Okay, so now we remove the B. Now this much table is left. Now what is minimum? Now the minimum time is 2, but it is in the machine 2. So you will allot on the last of the pallet. Okay, so as the minimum time is in machine 2, we have allotted job A on the right side of the pallet. Okay, so now A is allotted, so A will be removed from the table. Now out of the leftover table, what is the minimum time? You can see it is 3. It is in machine 1, so D will be allotted on the left side of the table. Similarly, removing D, now what is minimum? It is 4. It is on machine 2, so E will be allotted on the right side. And finally C is left, so it will be allotted as the center. In this way, our pallet is completed with the sequence of B, D, C, E, A. Now this is the optimum sequence as per the minimum processing time. Now what about scheduling? Okay, now this is the scheduling. Now this table is to prepare, this is called as a scheduling table. This is to be prepared as per the processing times and some rules. Okay, so what is this table containing? It is containing 3 columns for every machine. Column 1 is in time in that machine. Column 2 is out time for that machine. Column 3 is idle time of the machine. Similarly for machine 2 also, in time for the machine, out time for the machine, and idle time for the machine. Now how to fill up these values? So for filling up this table, you have to keep this table with you having processing times. Okay, so how to fill up this table? There are 2 rules. In time for machine 1, first of all, in time for machine 1, okay, it is very simple. Out time of machine 1 will be the in time of machine 1 for the next product. You can see here. Okay, I am repeating it. Okay, in time of machine 1 for any product will be the out time of machine 1 for the previous product. Okay, so you can see this 1 1 4 4 13 13 23 23. Okay, but for machine 2 there is a criteria. In time for machine 2 will be maximum of 2, out time of machine 1 या out time of machine 2. So out time of machine 1 of current job या फिर out time of machine 2 of previous job, इन दोनों में से जो maximum रहेगा that will be in time for machine 2. We will see here. Okay, and the formula for idle time is in time of current job minus out time of previous job. Okay, so how to fill this table? So our sequence is B D C E A. From the palette we got it. This is not our sequence. Okay, this is our sequence B D C E A. You can see it here, B D C E A. So first we'll arrange the jobs as per the sequence of palette. Then definitely for the first job the in time will be 0. It will start immediately. Now how much is the processing time of product B for the machine 1? We can see here it is 1. So if the in time is 0, what will be the out time? In time plus processing time. So 0 plus 1 will be out time. Now for machine 1 it is simple. Out time of product B will be the in time of product D. I am talking about machine 1 only. Only concentrate on machine 1. So the starting time is 0. Starting time plus processing time is 1. So out time is 1. If the out time of product B is 1, then in time of product D is also 1. Then what is the processing time of product D? It is 3. So 1 plus 3, 4. So 4 is the in time of product C. What is the processing time of product C? You can see here 9. So 4 plus 9 is 13. 13 is in time of the product E. Then what is the processing time of product E? 10. So 13 plus 10 is 23. So 23 is out time of product E as well as in time of product A. In this way you will get all the values filled for machine 1 very easily, because it is a machine 1. It is always idle after processing one product. But for machine 2 there is a criteria. What criteria is there? So first of all, what is the in time for machine 2? Out time of current job or out time of previous job. So for the first job there is no previous job, so it will be the out time of M1 of current job. What is the out time of M1 of current job? It is 1. So in time will be 1. Now what is the processing time of machine 2 of product B? It is 6. So 1 plus 6, 7. Now here you cannot take 7 directly, you have to check. Okay, so there is, what is the out time of current job for machine 1? It is 4. But what is the out time of machine 2 of previous job? It is 7. So 4 and 7, what is maximum? 7. So 7 will be the in time of machine 2 for job D. Then 7 plus processing time of D in machine 2. So 7 plus 8, it is 15. Now 15 cannot be taken directly. We have to see current job ka machine 1 is 13, previous job ka machine 2 is 15, which is maximum 15. So what is maximum out of 13 and 15? 15. That's why 15. Now here you will understand. If in time is 15, what is the time for machine 2 product C? It is 7. 15 plus 7, 22. Now 22 you cannot take here. So what is the previous machine 2 is 22 and current machine 1 is 23. So maximum you will take 23 here. Similarly for the next cycle 27 and 28, maximum you will take 28 here. Okay, and in this way you will get this table filled. Now idle time, in time of current job minus out time of previous job. Okay, for that machine. So idle time m1 will be always 0, or we can say that machine 1 is not idle because it is machine 1. How it can be idle? Okay, so it is in time of current job minus out time of previous job. So it is like this: 0 minus previous 0, so it is 0, 1 minus 1, 0, 4 minus 4, 13 minus 13, 23 minus 23. But here it is like 7, here in time of current job minus out time of previous job. Okay, so 1, it is started at 1. So machine 2 was waiting till 1 minute because it is dependent on machine 1. So initially there is idle time of 1. Then 7 minus 7 is 0, 15 minus 15 is 0, 23 minus 22 is 1, 28 minus 27 is 1. In this way we get the values of idle time for machine 2. Okay, now what to do with this value? Yes, the last time, okay, last job ka last machine ka time. What is the last machine? M2. And what is the last job? A. So this is called as total elapsed time. This is the total time taken by both the machines to produce all the jobs. Okay, so this is called as total elapsed time. So total elapsed time is 30 hours and total idle time on machine 2 is 1 plus 1 plus 1, that is 3 hours. And total idle time on machine 1 is 0 because it is machine 1, there is no idle time. Now next we will go to n jobs and 3 machine problem. This was n jobs and 2 machine problem which we discussed. Now what about 3 machine problem? So first of all, you cannot solve any 3 machine problem by Johnson's algorithm. First you have to check the eligibility. First you have to check the eligibility. So there is some primary criteria which is to be checked for every 3 machine problem. If this criteria doesn't meet, you cannot solve it by Johnson's algorithm. Okay, so there are 3 machines, M1, M2, M3. Each job has to go through 3 machines. So this is the criteria. First ये आपको चेक करना पड़ेगा, अगर इनमें से एक भी कंडीशन सेटिस्फाई हो जाती है, एनी वन और बोथ, दोनों होती है या दोनों में से एक भी कंडीशन सेटिस्फाई हो जाती है, देन you are able to solve that particular problem by Johnson's algorithm, otherwise not. So this is the first step. Whenever you see any problem more than 2 machines, first you have to check this criteria. If this criteria doesn't meet, don't waste your time by attempting it by Johnson's algorithm. So what is the criteria? Minimum processing time on machine 1 should be greater than or equal to maximum processing time on machine 2. And minimum processing time of machine 3 should also be greater than equal to maximum processing time of machine 2. Okay, we will see to it. Then after checking, if any of this condition is satisfied, you are able to solve it. But how will you solve it? We have the Johnson's algorithm. Okay, we have the palette logic for 2 machines. So what you do, you now convert your 3 machine problem into 2 machine problem. So 2 hypothetical machines are considered, PMM1 and PMM2. You must have heard this perpetual motion machine, right? क्योंकि एक्चुअल प्लांट में तो 3 मशीन्स है. अब हम सिर्फ उसको हाइपोथेटिकली कन्वर्ट कर रहे हैं 2 मशीन में फॉर सॉल्विंग इट बाय जॉनसन्स एल्गोरिथम. एक्चुअल में वो 2 मशीन तो हो ही नहीं सकती है क्योंकि हमारे प्लांट में 3 अलग अलग मशीन है, M1, M2, M3. लेकिन उसको सॉल्व करने के लिए हम 2 परपेचुअल मोशन मशीन बना रहे हैं, इमेजिनरी मशीन्स बना रहे हैं, ताकि हम उसको जॉनसन्स एल्गोरिथम से सॉल्व कर पाए. जस्ट टू गेट अ सीक्वेंस. ओके, ये परपेचुअल मोशन मशीन्स से हमको सीक्वेंस मिल जाएगा, लेकिन शेड्यूलिंग हम तीनों मशीन्स का ही करेंगे. वी विल सी हाउ टू डू दैट. ओके, सो कंसिडर 2 हाइपोथेटिकल मशीन्स, PMM1, PMM2, and get the resultant processing time. सिंपल है, 3 मशीन्स का टाइम है हमारे पास, मतलब 3 कॉलम्स है. सो यू ऐड फर्स्ट 2 कॉलम्स टू गेट द टाइमिंग्स फॉर PMM1 and you add last 2 columns for getting the timings for PMM2, and in this way your problem will be converted into 2 machine problem, and just you have to solve it like a previous case. Okay, but only scheduling for but only sequencing for scheduling you have to do for 3 machines. Okay, so let us proceed. See, this is a 3 machine problem on the screen. There are 5 jobs A, B, C, D, E, but there are 3 machines. So first we will check the condition. What is the condition? Primary condition, minimum processing time on M1. What is it? M1 का minimum processing time कितना है? 3. Okay, should be greater than equal to maximum processing time of M2. M2 का ये कॉलम है, इसका maximum कितना है? 5. So 3 is greater than equal to 5. Condition is not satisfying. Okay, 3 is not greater than equal to 5. So पहली कंडीशन तो मेरी सेटिस्फाई नहीं हो रही है. Now we will also check second condition because दोनों में से एक होना जरूरी है. तो सेकेंड कंडीशन क्या बोलती है? मिनिमम प्रोसेसिंग टाइम ऑफ M3. 3 का मिनिमम कितना है? 3 का मिनिमम है 5. ओके, M3 में मिनिमम है 5. देयर आर 2 वैल्यूज बट मिनिमम इज 5. So 5 is greater than or equal to maximum of 2. Maximum of 2 is again 5. So 5 is greater than or equal to 5. So my first condition is not satisfying, but my second condition is satisfying. See, first condition 3 is greater than equal to 5. Wrong. But second condition is 5 is greater than equal to 5. So this primary condition gets satisfied. Once it gets satisfied, we will convert our 3 machine problem into 2 machine problem. How we got the values of PMM1? M1 plus M2. See, 3 plus 4 7, 8 plus 3 11, 7 plus 2 9, 4 plus 5 9, 9 plus 1 10. And how we got the value for PMM2? Last 2 columns, 4 plus 6 10, 3 plus 7 10, 2 plus 5 7, 5 plus 11 16, 1 plus 5 6. In this way we have converted our 3 machine problem into 2 machine problem, and rest of all procedure is same. Then you make a palette logic से उसमें sequence बनाइए. लेकिन जब scheduling करेंगे then you have to take 3 columns for 3 machines, but the logic is same. Okay, for scheduling the logic is same. So what we are doing? We are converting our 3 machine problem into 2 machine problem. Similarly we can do if there are n machine problem. There are 6 machines here, you can see on the screen. इसका भी हमें वो ही लॉजिक से वो ही करना है. We have to convert this problem into 2 machine problem. Okay, how we will do this? Primary condition, यहाँ पे कंडीशन चेंज क्या हो जाएगी? पहला रहेगा मिनिमम प्रोसेसिंग टाइम ऑफ M1 शुड बी ग्रेटर देन इक्वल टू मैक्सिमम प्रोसेसिंग टाइम ऑफ 2 3 4 5. नाउ सी हियर, दिस इज 1 मशीन, दिस इज मशीन 2, एंड ये बीच की चारों मशीन को हम मिला के पकड़ेंगे मशीन 3. तो पहले हम इसको समझेंगे कि हम इसको 3 मशीन प्रॉब्लम में कन्वर्ट कर रहे हैं और फिर उसको 3 को 2 मशीन प्रॉब्लम में कन्वर्ट कर रहे हैं. तो देखो मिनिमम प्रोसेसिंग टाइम M1 कितना है? 11. इट शुड बी ग्रेटर देन मैक्सिमम प्रोसेसिंग टाइम ऑफ 2 3 4 5 कॉमा कॉमा करके. सो 2 का मैक्सिमम कितना है? 8. 3 का है 9, 4 का है 6, 5 का है 10. सो 11 इज ग्रेटर देन, इसका सम नहीं अलग अलग, 11 इज ग्रेटर देन 8 9 6 10. सबसे बड़ा है 11. यस, कंडीशन सेटिस्फाइड. अब अगर पहली सेटिस्फाई होती है तो दूसरी चेक भी नहीं करनी होती है, बिकॉज आइदर ऑफ द वन इज इंपॉर्टेंट, बट स्टिल वी आर चेकिंग द सेकेंड कंडीशन. मिनिमम ऑफ मशीन 6, लास्ट मशीन कितना है? 12. So 12 is also greater than 8 9 6 10. So both the conditions are getting satisfied. Now how to convert it into 2 machine problem? For PMM1 it is the addition of 1 plus this 4. So you can see 18 plus 8 plus 7 plus 2 plus 10, it is 45. Okay, 17 plus 6 plus 9 plus 6 plus 8, it is 46. So addition of first 5 columns is PMM1 and addition of last 5 columns is PMM2. Okay, in this way we have converted the n machine problem into 2 machine problem. What to do after 2 machine problem? Normally by Johnson's algorithm you can solve it. Now one more question arises after understanding the complete Johnson's algorithm, that what to do when we get a tie. Okay, in Johnson's algorithm it says that minimum time is in machine 1, so allot the job to the left side of the pallet. Minimum time is in machine 2, so allot the job in the right side of the pallet. But what if there are similar values sometime? Okay, or there are 2 minimum values. Okay, so these are some of the tie breaking rules which are suggested by the proposer of the Johnson's algorithm, that what to do when you get equal value. Okay, so here LPT means the least processing time, और या हम उसको shortest या minimum processing time बोलते हैं. If there are equal LPT on both the machines, okay, so on both the machines you get equal processing time. So job on machine 1 first in the sequence and job on machine 2 last in the sequence. You follow this rule if you get equal values on both the machines. Now if there are 2 equal values on machine 1, okay, on the same machine there are 2 minimum values. So if the minimum time is 2 but it is for 2 products, then select the job with LPT in M2. Okay, दोनों में से जिस भी जॉब का मशीन 2 का कम टाइम है उसको पहले लगाओ सीक्वेंस में. एंड थर्ड रूल इज इफ देयर आर 2 इक्वल LPT on M2, select the job with LPT in M1 for placing last in the sequence. Okay, so these are the tie breaking rules which are to be considered when you get equal values. So first you have to understand the process and procedure of Johnson's algorithm, and then if कहीं पे अगर tie होता है, so these 3 rules are for tie breaking. Okay, so you can go through these rules very cautiously. If you get a tie, accordingly आपको वो sequencing का procedure वहाँ पे follow करना है. So that's all about today's lecture. Thank you and have a nice day.